We get energy into our circuits using sources, and the first type of source that we're going to look at is the ideal voltage source. So an ideal voltage source is one that maintains a specified voltage at its terminals. So we draw it with a circuit symbol that looks like this. So we have a circle, we draw a little plus and minus, and we label the voltage nearby. So as an example, that would be a 12-volt source. We could then connect that up to the rest of our circuit, kind of whatever other components that we have, and that would then be a depiction of the electronic system that we would like to study. So this component here, this is an ideal source. So ideal sources are basically perfect. What that means is it will always generate the specified voltage. It's kind of a mathematical approximation, the absolute best case scenario. Ideal sources are perfect. This source will always supply 12 volts regardless of the amount of current that it is asked to produce. So when I say asked to produce, what I mean is that the rest of the circuit here is going to influence how much current, how much power is actually needed here. And so if I have an ideal source, we're saying that it's always going to be 12 volts, kind of regardless of what else is going on. An important point to recognize is that ideal sources cannot exist in real life. This is an approximation. Right, this is an approximation that we use because it simplifies our mathematical modeling. So a real voltage source has some limits, right? It can only supply a certain amount of power, whereas an ideal source, we're basically neglecting all of that. And so that makes things easier, particularly as we're starting to analyze circuits. So an important point about ideal sources is that the current that is supplied by that voltage source is actually not that easy to know, right? You have to actually analyze the rest of the circuit in order to figure out how much current will be supplied. So let me make a few comments about this. So the current generated by an ideal source, I should say voltage source, an ideal voltage source. An ideal voltage source is not obvious. And you have to do some calculations, and we're going to learn in future videos some rules that you can use to do those sorts of calculations. But basically there's a little bit of work needed to figure out the current. The voltage is easy. The voltage, of course, is just written on the component. So this would be a 3-volt source. But if you wanted to know, let's say I'll hook this up to some circuit, I'm just going to draw a little box here that indicates there's some other components. I'm not saying what those are right now. If I wanted to know what was the current here, this current I, some work would be needed. I would actually need to analyze the rest of my circuit in order to calculate what is that current. So there's also the concept of a current source. And so a current source will maintain a specified current through its terminals, and it will do this kind of regardless of the voltage. So we draw a current source with a symbol like this. So we draw a circle that indicates a source, and we draw an arrow that indicates a current, and then we label it with the amount of current. So for example, 2 amps. And again, we would hook this up to some other circuit, basically saying that there's some other parts over here. And now we know that there will be 2 amps flowing along this wire, and that's kind of by definition of what this current source will do. Now, again, all of the kind of caveats of ideal sources apply here. So this is something that will always maintain this current, but it can't exist in real life. So a real life current source has limits, and we're saying here that we're just neglecting those. The voltage that is supplied by a current source will depend upon the rest of the circuit. So if I take a simple example, if I have here a current source, maybe I draw it that way, and then I hook this up to, again, there'll be some other components, not specifying yet what those will be. I would have to actually go and analyze the rest of this circuit if I wanted to know what is the voltage across that current source. The voltage across the current source, by the way, I mean something like this. So a voltage that you would measure if you had connected a multimeter kind of across the pins of that current source. So in other words, I have my multimeter, and it has these wires, and I take one wire and I put it here, and I take another wire and I put it here, and I do that sort of measurement. So this depends on the rest of the circuit. So again, this is not obvious, and you have to do a little bit of work in order to know the voltage that is supplied by a current source. Now, sometimes we write sources which depend upon some other variables. So as an example, what I can do is I can define a voltage source. Now, by convention, if it's a dependent source, dependent meaning that there's some mathematical expression that it is controlled by, then we use the kind of diamond shape that you see here. So I can write here some variable. So I can write like 2I0, and we're saying here that this produces a voltage which is equal to this mathematical formula. And then I would need to have somewhere else on my circuit, I would need to have that I0 variable labeled. So as an example, if I had something like this, and I say, all right, the current that flows in here is called I0, then now this becomes something that is kind of well posed. And mathematically what I can do is solve for what is this I0 value, and once I know this I0 value from here, I can then substitute it in to calculate what is the amount of voltage that I will have over here. So these things are called dependent sources. We can also have dependent current sources. So let me just make a note here. So this is a dependent voltage source, and I know that it's a voltage source because it's labeled with little plus minus. Dependent voltage source, and that's because it has the little plus minus. I could also draw something like this, so I use the little diamond shape again, and I can put a little arrow on it, and then I can again write some mathematical expression. So let's say 5I0. I0 has to be defined elsewhere in the circuit. This component here is a dependent current source. And again, I know that because it has the little arrow drawn inside of it. So these examples here are controlled by a current value. So I know that it's a current value because I'm using the variable I, which by convention will be current. Also, I could read the rest of the circuit and I could observe that it's annotated in that way. So we could call these current controlled sources. So the kind of full name for this first component, if you really want to kind of spell it out in full detail, you could say that this is a current controlled voltage source. And the bottom one is a current controlled current source. So we can specify it like that. Now these are mostly used in modeling of more complicated circuit components. So as an example, there are some kinds of transistors that behave like controlled current sources. And so we can create a mathematical model and analyze them using these sort of tools. And that's why you're sort of learning about that concept at this stage. But as far as analyzing them, it's pretty straightforward. It's just a mathematical expression. So you're just going to write down the equations and then kind of use algebra to solve what the resulting values will be. Now, a final point that I wanted to make while we're talking about sources is the difference between direct current DC and alternating current AC. So DC is a kind of commonly used term, which basically means a voltage or current that doesn't change with time, or if it changes really slowly. So I can draw a little graph, and I can say the voltage supplied by my power source as a function of time, and it's constant. So that is DC, direct current. So we call it direct current, even though most of the time we talk about voltage sources. So it should really be something like constant voltage. But anyway, the terminology is historical and it's kind of stuck. So that just means a voltage current that is fixed in time. And that is what we will study in this class. So all of EG1012 will study DC. So DC sources include so batteries. A battery produces a direct current, so a battery is kind of like a voltage source. The DC sources include batteries, solar panels, the bench supplies that we will use in most of our pracs. So these things all supply DC, direct current. On the other hand, AC means a voltage and current that varies sinusoidally. Okay, it's like y equals sine x. I'll draw a little plot. So I could have voltage versus time, and it looks like this. It's like a sine wave. So this is AC. So AC, you may know, is used in the mains power system. Mains power system. So when you plug into a power point, you are connecting to an alternating current source. It's an AC current source. All the power lines that you see out in the street when you're driving, those are all carrying alternating current. So AC is used basically, again, it's kind of a historical reason, but one of the main advantages of alternating current is that you have simple machinery for generating it. So it's used for the large-scale power distribution and the whole mains power system, but we are not going to study AC in this subject. So we can actually use many of the same tools, but there's a little bit of mathematical complexity because of this sinusoidal variation. And so that's a topic that we will reserve for a future subject. But in this subject, we're dealing with what we call DC, direct current, basically constant voltages and currents. So they are not sinusoidal, they're not varying as a sine wave.